Question number 57 is a beautifully AP problem because it requires us to remember not only the current impulse momentum / collisions material, but we will also be referring to uniform circular motion and conservation of energy during this. So let's first analyze what's going on. We have two objects right here. One of them is at rest and the other one is moving. The smaller one with the small m is colliding with an object that is a big M, and then they tell us that the collision can be either perfectly inelastic when they stick together or perfectly elastic, which means that no energy will be lost, but only the big object with the big M is going to go up in the loop. The second part, how are they going in that loop? We'll allow the second block to circle the loop without falling off. So that means even though they say only the second block, if we're saying perfectly inelastic, that means both of them. But if it's perfectly elastic, then indeed we are only talking about the second one, without falling off the loop-to-loop. Remember from uniform circular motion, the minimum speed with which it can complete without falling off is when almost no contact with track, so therefore mg is the only force that is acting on our object. And I'm using m here in just general sense. I'm not referring either to the little m or to the big M from our particular problem, just the general force of gravity. Let me put it that way so you're not confuzzled. Here's our point of reference. Fg in this case is going to be your centripetal force. It's going to be, I'm going to use the curly m times v squared over r, and it would be equal to the curly m times g. I'm using curly because it can in A mean big M plus small m, and in B it will be just the big M because the little m bounced off and did not continue on to the loop. Let's write it out. Cancel m, therefore v squared equals gr. All right, so that's from uniform circular motion. Let's go to the understanding that after the collision, they start moving, both of them together or that big M. And as they start moving, they only have kinetic energy initial. Right here, they have kinetic energy final, and they have gravitational energy, or our object, whether it's two or just one. Therefore, I can say that this right here is the V final, for that matter, at the top of the loop. I can say that my K initial equals K final plus UG, and K final plus, if I am at the top of the loop, that is my curly M G2R, because that's my height. That is mu GH, not mu M. Just curly M. Now let's think about what we're dealing with in terms of kinetic energy. So kinetic energy initial is my curly M times V initial squared over 2. That is right after the collision. That right here is my curly M times V final squared over 2. But we already referred to that V final squared as GR, so I can replace this as my curly M times GR over 2. Now let's put it back together. I'm going to put this in terms of kinetic energy final, and then here I also have my mg plus 2r. So let's look at our curly m v initial before the collision squared over 2 should be equal to my curly m, and then I have my gr over 2 for kinetic energy plus 2gr for potential energy. That's 2.5 gr. So I'm going to say it's m times 2.5 gr. If I cancel my m's, I know that my v initial should be equal to 5 gr. And let's look at our perfectly inelastic collision. Perfectly inelastic collision, and I'm going to use the actual m's that are given to me. Mass of my moving object is about to collide with the big one, which is at rest right now, should be equal to the sum of them, the little m plus the big M, times V final. V right after the collision squared should be this one. So I'm just going to say that this would be M V M initial should be equal to M plus big M times root of 5gr. If I found this to be 5gr, but in my formula for conservation of momentum, it's not squared, just V, then I have to root the 5gr. The minimum initial velocity of the little object that is about to collide with the big object at the bottom of the loop, root of 5gr times the sum of the masses over the little m. This would be only for perfectly inelastic collision. What if the collision is perfectly elastic? Mind you, nothing changes in terms of what happens with the loop-to-loop. The only difference there is that our mass, instead of the collective mass, it would be just the little m. The required velocity, as you see right here, the required velocity had nothing to do with the mass. Now, what do we know about collision that is perfectly elastic? So in perfectly elastic collision, what I would have is my little m times its v initial, which I am after, should be equal to mass times v final, which I am not sure what it is, plus 5gr when it's squared. So this is going to be the big mass times, and then I have my root of 5gr. Problem is, I have now one equation, but two variables. I don't know my initial or my v final, and it's only one equation. You have two options. You have an option to go into kinetic energy initial equals kinetic energy final. Now I have two equations and two variables. What I can do, I can express my v initial squared through these two and replace. I can also square my top equation. I can do all kinds of things. It would require lots and lots of math. Now, what you remember, hopefully, is that approach velocity, or rather speed, should be equal to separation velocity for elastic. So again, when we have two objects that are approaching each other, so let's say I have two objects that are colliding, and they're heading towards each other 5 meters per second, and then the other one is, let's say, 7 meters per second. Then, when they start separating, if I look at this, they are approaching is 12 meters per second. Then they should start separating. So if I say that this guy goes with 7 now, then that guy has to go with 5 in order for this collision to be indeed elastic, or approaching speed, I should say, is 12 meters per second, then the separation speed should also be 12 meters per second. So applying the rule for separation and approaching speeds, I can say that my v initial for the little one plus 0, this would be my approach speed, equals, and then if I'm going for separation, this is my v final for the baby one, this is my root of 5gr for the big one, right? 5gr is the positive. V final is rebound speed, so I should subtract it in order for me to get, because look at this. This one was positive, right? So if I do positive plus 0 is a positive number. So if I want to get my vectors straight, root of 5gr minus V final, okay? So now I'm in good shape because now I have two equations and two variables. That is very solvable. So what are we going to do? Because I'm looking for V initial, I'm going to express V final through a root of 5gr. I'm just going to take this to the left with a plus minus V initial. So that's just rearranging my second equation right here, equation number 2. Then I'm going to grab my equation number 1 and replace V final in it with this. So then I end up with mv initial equals m, and then I have my root of 5gr minus V initial plus big M root of 5gr right here. If I distribute, I will get my M and V initial with a minus, which I will then put it on the right side with a plus. So I'm going to end up with 2mv initial equal. And then when I distribute this, I have my 5gr root twice. So I'm just going to factor the two masses together and then 5gr. Therefore, what am I going to do? Well, I'm going to just rearrange my V initial. It's going to be 1/2 of, similar to what we had before, the sum of masses plus over little m times root of 5gr. So this would be the minimum velocity for an elastic collision. So it's going to be 1/2. Before, we had it to be equal to 5gr. When it's elastic, it just needs to be half of that.